Buildings are among the world's biggest energy consumers. They significantly contribute to fossil fuel consumption and are responsible for a large proportion of CO2 emissions. While existing buildings are often difficult to renovate sustainably, new buildings present a huge opportunity for energy transformation. Simply making buildings energy efficient or carbon neutral is no longer enough. They should actively contribute to energy production and grid stabilization. The IFU Institute for Environmental Energy and the company Equitronic have joined forces to explore how buildings and entire neighborhoods can be transformed into sustainable energy generators. True to the motto, buildings as power stations, the result is a completely new standard in energy conversion, active energy. Unlike previous energy standards such as passive house and active house, which set strict requirements for insulation, ventilation, and construction methods, active energy presents a clear goal. Buildings must generate more energy than they consume. How this is achieved is left open, and this is the strength of the standard. It allows room for innovation and new approaches. Active energy sets 4 key objectives. Buildings built to the active energy standard will generate at least twice the energy they need, using only the sun's energy. They are CO2 positive, both in construction and in operation. They don't just avoid CO2 emissions, they actually reduce them. Resource-saving building materials ensure that at least 50% of the components can be directly reused during dismantling. The majority of the rest can be recycled. Excess energy is efficiently stored to meet winter demand. It is specifically stored in the electricity and heating networks to ensure a sustainable energy supply and stabilize the grid. It sounds impossible, but it can be done. Solar energy is free and abundant everywhere. The annual solar energy that shines on a single-family home with 150 square meters of roof area is 150 megawatt-hours. In comparison, the heating requirement is 20 megawatt-hours and an electricity requirement is 7 megawatt-hours. The total energy produced, both heat and electricity, is more than 5 times the energy required. If this energy could be harnessed, the house could not only provide energy for itself, but also for other houses. Photovoltaic thermal energy, PVT, is a proven technology that generates both electricity and heat from the sun. But Equitop Thermo PV takes this technology a decisive step further. The company Equitronic has succeeded in developing an integrated roof and facade system of individual PVT modules. Conventional roofs and facades are replaced by a highly efficient large-area heat exchanger. This is covered with glass PV modules, eliminating the need for additional separate PV modules. This means that the roof and facade become a single, powerful energy source that generates electricity and heat at the same time. The heat generated is transferred directly to the heat pump. This is a classic geothermal heat pump that can be used with both radiators and underfloor heating systems. An energy center connects the roof and facade system and the geothermal system to the heat pump via brine pipes. This means that the optimum energy source can always be used, where excess heat from the photovoltaic system can be stored, without having to operate the heat pump. Thanks to this innovative solution, almost all the solar energy that reaches the building can be utilized without the need for additional space for separate solar modules. Active energy thus turns buildings into highly efficient, grid-active small local power stations. Here we see an example of how an active energy system can be constructed. First, the substructure is mounted on a CLT, cross-laminated timber, construction panel. This forms the base of the energy system and ensures stability and optimal integration of the following components. On top of this is the Equitop heat exchanger layer. This consists of individual extruded modules that are assembled to create a high-performance, large surface area heat exchanger that also forms the building envelope. Each of these modules is fitted with brine pipes connected to a manifold. This allows the absorbed thermal energy to be efficiently transported and either used immediately or stored for later use. Glass PV modules are applied as the final layer. This creates a complete roof module. This combination ensures that the roof and facade generate electricity and heat at the same time, actively contributing to the energy supply. The system is not limited to CLT buildings, but can be implemented in all common building types, particularly in combination with CO2 positive and reusable CLT. The result is an industrially prefabricated modular construction method that significantly speeds up the construction process and makes it more sustainable. It is also suitable for serial refurbishment. Quick and efficient installation thanks to complete modules. This slide illustrates how the active energy system is installed in practice. The use of complete modules, consisting of a CLT wall or roof structure that also incorporates the energy and facade or roof systems, can significantly accelerate the entire construction process. Both the load-bearing wall or roof modules and the energy generation systems, in the form of integrated PVT roof and facade panels, are installed in a single step. These complete modules can be prefabricated in sizes of up to 3 by 16 meters and assembled directly on site. This enables efficient, precise, and extremely fast construction. The modular construction method not only reduces construction costs, but also achieves a particularly high level of energy efficiency and sustainability, thanks to easy dismantling and reuse. Underground geothermal energy is a space-saving solution. Traditionally, geothermal systems are not installed directly under buildings. This is because conventional systems rely on natural regeneration from summer rain and environmental energy. This regeneration cannot take place when the system is installed under the floor slab. The active energy system takes a completely new approach. Our buildings generate many times more energy than they need through their facades and roofs. This surplus energy is not wasted, but is actively stored in the ground before the winter season. Positioning the geothermal system directly under the floor slab offers decisive advantages for new buildings. Low costs. In new buildings, the geothermal storage tank can be installed directly under the floor slab without the need for additional earthworks. The floor slab acts as natural thermal insulation, which means that the stored energy is not lost. Year-round energy availability. Instead of relying on natural regeneration, geothermal energy is specifically charged with solar energy from the summer. High source temperatures even in winter. While traditional geothermal systems often only reach source temperatures of 3 to 7 degrees Celsius, the active energy system starts the coldest months at 20 to 25 degrees Celsius. This innovation creates an energy island directly under the building. This allows buildings to be efficiently supplied with sustainable heat all year round, without recourse to fossil fuels and without dependence on external sources. In old buildings, installation under the floor slab is no longer possible. However, costs are saved as the storage tank can be smaller. There are different operating conditions throughout the year. Thanks to the combination of geothermal energy and PV heat surplus, our system is perfectly prepared. In spring, heating with PV heat surplus. After the winter, the geothermal storage tank has cooled down. When the sun shines, the PV modules heat up. Their excess heat is transferred to the heat pump via the heat exchanger and used to heat the house and provide hot water. The high source temperature ensures low electricity consumption. In summer, passive heat storage, without a heat pump. When the building envelope generates excess heat, it is transferred directly to the buffer or ground storage tank, without the need for a heat pump. In summer, passive cooling. As long as the underground storage tank is not too hot, natural cooling is possible without an active heat pump. The cooling energy also heats the underground storage tank. In autumn, active cooling. If the underground storage tank gets too warm, the heat pump provides cooling. In winter, geothermal heating. If there is a need for heating and the PV modules do not produce enough heat, the geothermal energy is used. The pre-storage has increased the temperature of the geothermal storage tank, and the electricity demand is now lower. As only a third of the annual heating energy is obtained in this way, a small geothermal storage tank is sufficient. But even in winter, the PV modules often generate enough heat to keep the house warm. In winter, defrosting the PV system. Is there snow or ice on the PV system? No problem. The system can be defrosted using stored geothermal energy without any additional energy consumption. Year-round grid-active heating during power surplus. When surplus renewable electricity is available, it is used to generate and store heat, even when there is no demand. Year-round grid-active heating during power shortage. When there is a shortage of renewable electricity in the grid, this stored heat can be used. This reduces the load on the grid and increases security of supply. This makes the heating system grid active for the electricity system. Whenever there is a shortage of renewable electricity, the heating system shuts down. With this sophisticated system, we are creating a sustainable energy supply that is efficient, flexible, and environmentally friendly. New energy supply with Equitop Thermo PV and activenergy. The way in which buildings are supplied with energy has hardly changed in recent decades. Until now, different systems have been combined to produce heat and electricity, often leading to high investment costs and inefficient solutions. Traditional implementations rely on a variety of energy sources, including air source heat pumps with high electricity consumption, CHP, and biogas plants that use fossil or renewable resources. Wood chip heating systems with high maintenance costs, deep boreholes, and energy farms with significant development expenses, and finally, open space photovoltaics that require additional land. These systems not only result in high operating and maintenance costs, but also often require complex management structures to operate the infrastructure. With Equitop Thermo PV and the active energy concept, this is now easier, more efficient, and more sustainable. The sun is free. Instead of fossil or biogenic fuels, solar energy is used directly. Equitop replaces conventional roofs. The entire building envelope becomes an energy generator for electricity and heat. Efficient heat storage. A heat exchanger under the foundation slab stores excess heat for the winter. Cold district heating networks. These provide highly efficient energy distribution as buildings are supplied from their own storage systems. No additional land use. Energy production is fully integrated into the building structure. This new, fully integrated solution eliminates many costly and inefficient intermediate steps. Buildings become energy self-sufficient while stabilizing the electricity and heating grid. At the end of their useful life, buildings are designed for dismantling. At least 50% of the building components can be reused, while the remaining materials are largely recyclable. The active energy standard defines the buildings of the future, regardless of their use or size. This system is suitable for a wide range of building projects. Residential buildings, single-family homes, apartment blocks, and modern neighborhoods. Commercial and industrial buildings, factories, manufacturing plants, and office buildings. Supermarkets and retail outlets. Buildings with high energy consumption and cooling requirements. There is a particular advantage in buildings with cooling requirements, such as supermarkets, data centers, or industrial cooling systems. Here, the otherwise unused heat surplus from the cooling systems is used in a targeted manner. Direct use in building heating. The heat surplus is efficiently integrated into the heating system. Future developments will benefit from significantly lower development costs. New forms of grid stability and combined heat and power are also possible. This single-family home near Lake Constance was equipped with a modern energy concept in 2022. The roof features a south-facing photovoltaic system with a capacity of 5.5 kilowatts. Heating is provided by a 9 kilowatts heat pump, which draws energy from a ground collector covering 60 square meters, consisting of 6 loops, each 80 meters long, installed 10 centimeters below the floor slab. The project demonstrates how renewable energy can be efficiently integrated into new buildings with Equitronic. In 2022, the energy concept of a building near Lake Constance was analyzed. The total heating demand was 25,560 kilowatt-hours, with 17,250 kilowatt-hours from the PVT system and 8,310 kilowatt-hours from geothermal energy. The heat pump required only 3,090 kilowatt-hours of electricity, with a COP of 8.27. Just 38% of the electricity came from the grid. The remaining 61.9% was generated by the building's own PV system. This resulted in savings of around 2,440 liters of heating oil. In addition, 4,500 kilowatt-hours of solar power were available for household use or charging an electric vehicle. A strong example of how renewable energy can be used efficiently in new buildings. Insulation is installed between the rafters to retain heat inside the house and improve energy efficiency. A waterproof membrane is then laid over the insulation layer. Aluminum battens and counterbattens are mounted onto the rafters as the base for installing the EQ16 thermal profiles. The EQ16 thermal profiles are made of extruded aluminum and are installed one by one using a simple click-in system. They snap precisely into place, are carefully aligned, and securely locked using special spring elements to ensure a stable and durable structure. Next, the PV modules are carefully placed on the closed surface and precisely aligned. They are securely fixed in designated screw channels using special clamps to ensure a stable and long-lasting connection. After the mechanical installation of the PV modules, the proper electrical connection is made to fully integrate them into the overall system and make them operational. At the same time, the hydraulic cooling pipes at the top and bottom are connected to the system and linked to the pre-assembled manifold. Finally, cover plates and additional accessories, such as rain gutters, are installed. The simulation shows the change in energy storage in the soil over a period of 2 years. This graphic shows the annual heating and electricity demand of a typical household. 20 megawatt hours for heating and 4 megawatt hours of electricity. As flow temperatures in the heating system increase, the heat pump has to work harder, leading to higher electricity consumption. Higher flow temperatures in the heating system require the heat pump to do more work, which increases the electricity requirement. The heat output of the heat pump consists of environmental energy, air or water, and the electricity needed to power it. The greater the difference between the source temperature and the heating flow temperature, the greater the latter. The annual coefficient of performance, COP, indicates the average COP for an entire year. It is significantly higher for the air source heat pump in the summer and can drop significantly in the winter. Consumption can be at its highest precisely when your PV system delivers the lowest yields. Equatronic can increase the SPF heating the ground. That depends on the storage temperature, volume, and tank quality. The Equatronic powerhouse combines solar energy, waste heat recovery, and smart storage to create an energy-efficient, sustainable home. With the demand calculator, users can enter their annual consumption, oil, gas, electricity, and heat, and estimate their solar potential using cadastre data. Based on this, the system calculates the required number of PV modules and the optimal battery size. By using waste heat and renewable electricity, the house achieves a balanced or even positive annual energy footprint, making it both eco-friendly and cost-efficient. This is an overview of our Equatronic Equitop Thermo PV grid, a 6th-generation district heating and cooling network. Whether it's a single-family home, a multi-family building, entire neighborhoods, or even industrial sites, with Equitop Thermo PV, you can turn any building into a true power plant. Our system achieves an annual electricity yield of 253.8 megawatt hours and an impressive heat yield of 621.8 gigawatt hours. That's enough to cover the electricity needs of around 36 single-family homes, assuming 7 megawatt hours per house, and the heat demand of about 31 homes, based on 20 megawatt hours each. Large industrial parks and sealed surfaces have enormous untapped potential. With Equitop Thermo PV, they can feed significant amounts of renewable energy into local heating and cooling networks, efficiently and sustainably. We have demonstrated how the new activenergy standard can be implemented. This provides a revolutionary solution for a sustainable and cost-effective energy supply. It is time not only to make buildings and entire neighborhoods energy efficient, but also to transform them into active power plants. With PVT technology, an alternative already exists that can meet this standard. But are there other solutions? Share this vision and help spread it through social media. We call on politicians to play an active role in its realization. Companies and developers should drive forward innovative solutions. We are looking for the first energy-positive neighborhood as a regional power plant. Who will be the first to join us?